All right, so today I'm pleased to welcome Tianhao Wang. Tianhao is our own graduate student. So Tianhao works with Ninghui Li in the computer science department. His research really focuses on the practical aspects of data privacy and security. He's published in several top-tier computer security conferences like Uniint Security and CCS, and his Erdos number is 3. Interesting fact. So today he's here to tell us about local differential privacy. This work is based on a recent Uniint security paper. All right, thanks.
All right, thank you, Jerma. So hi everyone, my name is Tianhao Wang. I'm a third-year PhD student in the CS department, and today I will present our paper on local differential privacy and frequency estimation. So this is joint work with Jerma, who is sitting over there, and my advisor Ninghui Li, and Professor Sumesh Jha from University of Wisconsin-Madison. Okay, so the background of this paper is called differential privacy, which is kind of the de facto notion in privacy preserving releasing of databases. So in this setting, there is one single data collector and a large number of users. The user will send the data to the collector, who will add noise and publish the database. And there exists some third party or some other government also who will do some data mining tasks on behalf of this noisy database. Yeah, so intuitively, different privacy means that the decision to include or exclude the individual's record has minimum influence on the total outcome. This is because of the noise. And the smaller epsilon means or implies the stronger privacy. So one issue here is that this centralized aggregator is trusted by everyone, because each user send the raw data to this collector. With the local differential privacy, which we investigate in this paper, hopefully this can be somewhat overcome. So in this local setting, everyone just add noise locally and before sending out to the database. So in this setting, there is no worry about the untrusted server. Right. So so I would like to take questions if you are confused or have any questions. Okay. Yeah. So actually, the local differential privacy notion, I guess, is the first deployed system. So this is the CCS 14 paper by Google. So they deployed the wrapper system, which is an extension of the Chrome browser. And it will collect users' preferences, like the default homepage and other configuration information. And also, Apple is deploying their different privacy system in our iOS or macOS operating systems. They use the system to collect data like typing information, like the word you typed in iMessage or other applications. And they also collect, like here, they collect the healthcare information like weight or blood information. Okay. Yeah. So this is the background, and here I will introduce the formal definition. So. Yeah, I guess I can move. So here are the two definitions: the DP definition and the lower one is the local DP definition. So in the in the classical DP, there is a randomized algorithm A, and we consider the original dataset D and its neighboring dataset D prime, and one output O, such that the probability that the randomized algorithm A output O on behalf of D is bounded by e to epsilon times the probability A output O on D prime. So this is the DP definition, and when it comes to local DP, we only consider any two inputs X and X prime, and any output Y. And notice that here in the classical DP, A is run by the server, while on the local setting, this randomized algorithm A will be run by each single person. So this is like add noise to this input, and it will go to Y. So I guess this notion may be too technical, but hopefully it will be more clear when we go to the examples. Okay. Yeah. So the first kind of technique for the local setting of different privacy is called the Warner model, which is proposed in 1965. It is a survey technique for private questions. Yeah, so the setting is, for example, if someone asks, are you a communist party? So for each single person, they may be afraid or embarrassed to answer such questions, but using this model, each person can answer this question while preserving his or her privacy, and the survey people will get a good understanding of the distribution. Okay, so specifically, the protocol works like this. So each person will flip a secret coin, and the person will answer the truth if the coin comes up head, and answer randomly if it comes up tail. For example, a communist will answer yes with 75% and answer no with 25%. If we work out the mathematics, because the truth is yes, and the secret coin will come up head with 50%, and for the other 50%, it will answer yes with another 50%, which is 25%. So adding these two together, we get 75%. And if the truth is yes, he will answer no. That means he will lie with 75%. So if a person is not a communist party, he will answer no with 75% and yes with 25%. Yeah. And to get an understanding of how many people are communists and how many not, we use these notations. Let n sub v be the number of users who are communist, and n is the total number of users. And therefore, n minus n sub v is the number of non-communist communists. Then we will expect to see 75% times n sub v plus 25% of n minus n sub v yes answers. So these users will answer yes. Yeah. So E is the expectation of the yes answers. So we will expect to see this number of yes answers. So C of n sub v here is the estimation of the centralized aggregator. So by this equation, C of n sub v should be unbiased, because if we do the estimation of C of n sub v, we will have this one, and E of I sub v is this one. It is this one. So if we do the math, we will have this is unbiased because this equation, this equals n sub v, okay? And yeah, so the good thing is this provides an intuitive definition called deniability, which means that after seeing the answer, the government or the survey people will not know for sure about each user, whether he or she is a communist or not. Yeah, so, and then we go back to the definition. The protocol is epsilon LDP if for any v and v prime, which could be yes or no, and v, the probability the user will answer truthfully divided by the probability the user will lie is bounded by e to epsilon. So if we use 70%, 75% as the denominator and 25% as denominator, e to epsilon should be 3. Okay. Then we can get epsilon. So this protocol is ln 3 LDP. Okay. Yeah, so one issue is this only holds for binary attribute. We will generalize it to the more generalized setting. So before we generalize, we can we look at the abstract protocol. So in this, ideally in this protocol, the user will have a secret value v from a big domain D, and there is a so this is the encoding function. The encoding function will take the v and output encoded value v value x. And then there is a perturb function which will get the encoded value x and output a value y. So notice that this p function here will satisfy epsilon LDP. And the value y is then sent to the third party who will run the estimation function that takes reports from all users and outputs the estimation for every value v in the domain D. Okay, so this is kind of how the protocol runs abstractly. And in this paper, we focus on frequency estimation. That means the only this EST function. Okay, so we focus on it because it's kind of the basic task in this LDP setting, and if we can improve this one, we will get better results for other, maybe more complicated tasks. Yeah, so before us, there are basically 3 techniques, but they all derived from the randomized response, derived from the randomized response mechanism. So the first one is we generalized the Warner model, which is reference 1 in 1965 by Warner. It's called the randomized response, and we call it direct encoding to differentiate it from the other 2. So the second one is introduced by the Google's wrapper paper in 2016. Okay, so we call it unary encoding, and the last one is 2015 stock paper by Basili and Smith. We call it BinaryLocal Hash. Yeah, so then now we look at them one by one. So the first one is generalized Warner model. So the original Warner model, I guess, we deals with the binary case. Now in the more general case. So consider a domain D of D possible answers. So the possible answers can be 1, 2, 3, up to small d. Then the user in this protocol will toss a coin with bias p. Okay, so we use the notion p here. And if the coin comes up head, the user will report truthfully y equals x, which equals v, because there is no encoding in this protocol. And otherwise, the user will report any other value with the probability uniform at random. So q is 1 minus p divided by d minus 1, right? Because, yeah, so to satisfy epsilon LDP, we need that e to epsilon equals, or I guess bigger than or equals p divided by q, which is this one. Okay. And by setting p and q to be these values, if we divide p and q, we will get exactly e to epsilon, right? And so here, I guess p here is the maximum possible value p can be. So the aggregator, on the other hand, will run this C function to estimate the number of users who have value v. So similarly, we use the n sub v as the number of users who have value v, and I sub v is the number of reports on v, and because expectation of I sub v is n sub v times p plus n minus n sub v times q, this C of v is unbiased. You have any questions? Okay. So the intuition is the higher p is, the more accurate it is. We will define the accuracy later. Okay. So, but notice that when D is very large, consider a very big domain, like for example H, it can range from 1 to 100 or more, or even more. Then this p-value will decrease, right? Because the D factor is in the denominator. Therefore, when D is large, the accuracy will be bad. So the second protocol we will introduce is this Uniint Coding. So in this protocol, the value v will be encoded into a vector of 0, except location v to be 1. So for example, if d is 1, 2, 3, 4, and the private value is 3, then the bit vector will be 0, 0, 1, 0. And similarly, to get e to epsilon local differential privacy, we kind of need this ratio to hold, and this ratio will be the so because each bit is independent, we need we can multiply them out, and in the end we get this one. So notice that p and q are the perturbation probability of of each bit. So with the probability p, each bit is perturbed, and with probability q, with probability p, the bit is preserved, and with probability q, it is perturbed. So with these p and q probabilities, we will get e to epsilon. Yeah. So this step is because each bit is perturbed independently, and then this step is because every x and x prime differ in at most 2 locations. And yeah, so the kind of intuition here is that by encoding the value into unary bit vector, each location can be only 0 or 1, then effectively each the domain is only 0 or 1. Therefore, the small d is 2 here instead of in the randomized response setting, the small d will be very large. So therefore, in this setting, no matter how large small d is, the privacy is the same because p is the same. P does not depend on d. Okay. Therefore, when d is large, this unary encoding will be better in terms of utility. Yeah. So after that, to estimate the frequency of each value, just do it for each bit. And here is an example. So suppose there are 5 users and they have value 2, 2, 3, 2, 4. And suppose the domain has 4 values, 1, 2, 3, 4. Then in the first step, each user will encode the value into the bit vector. So here 2 becomes 0, 1, 0, 0, and 4 becomes 0, 0, 0, 1. And then with the if we suppose this p and q values, each user will perturb the bit vector locally. So I guess 4 out of 5 bits will be preserved, and 1 out of 5 will be perturbed. So in this setting, none of the 4 bits are perturbed. And in this, the second user, notice that the second bit is perturbed from 1 to 0. And in here, the second bit is perturbed, and so on. Then each user just send y to the third party, who will first aggregate all the bits. So in the first location there is only one value 1, and in the second location there are, I guess, 3. So this is 3, and so on. Then the aggregator use this equation. So notice that I sub v is the value in each location. It's 1, 3, 2, 1. So after applying this equation, the aggregator get these values, which are the estimated count of the original distribution. Yeah, so kind of not very accurate, but when the number of users becomes very large, it will be pretty close. So the accuracy will increase with number of users. So the last protocol is called the BinaryLocal Hash. You have a question? No. It's called BinaryLocal Hash, and so now we describe a simpler version. So in this protocol, each user uses a random hash function from a big domain D. So the big D is the original domain, but the hash function will hash the domain into a smaller domain, 0 or 1. Like consider the mod 2. So 1357 will be hashed to 1, and 0268 will be hashed to 0. Then the user will perturb the bit with the probability p and q to be these values. So here assume g equals 2 here, but we will use this g value later. Okay, so if we use the p to the p equals e to epsilon divided by e to epsilon plus 1, and the q is 1 over e to epsilon plus 1. We will also have this equation to hold, which applies epsilon local differential privacy holds. The user then report bit 0 or 1 and the hash function. So this is one simpler example. Note, assume D is 1, 2, 3, 4, and the hash function for this user will hash value 1 and 3 into 0, and hash 2 and 4 into 1. Suppose the user has value 2, and which implies the hashed value will be 1, right? So the user then send to the third party that I'm in group 1, so the group 1 contains the values 2 and 4. Then the aggregator will add increment location 2 and 4. So similarly, we have this equation which is unbiased, and this expectation of I sub v is this value. So notice that this part will become different because we kind of partition the large domain into like 2 groups, and so if a user is not in the group, he will report either in the group or not in the group, because the hash function now is random. Yeah, so slightly more complicated the example is here. So similarly, consider small d equals 4, and the secret value will be 2, 2, 3, 2, 4. So consider here the hash function is the mod 2 operation, and each user will apply this private value plus his index. So assume each user has an index. So the user will apply v plus j, which is his index, and then mod 2. So in this setting, I guess I'm starting from 0. So user 0 is 0 plus 2 mod 2 is 0. So one mod.
I think you're starting from 1.
Oh yeah. It's 1 plus 2 mod 2 is 1, and 2 plus 2 mod 2 is 0, and 3 plus 3 mod 2 is 0. So then with this probability 4 over 5, that this is preserved. So 4 out of 5 will be preserved. That's user 1, 2, 3, 4, right? And the last report is perturbed from 1 to 0. Then each user will send this value to the aggregator, who will first recover the vectors. Okay, so because the aggregator knows this function, so we assume this function is public, but it is random. Okay, so then the aggregator will know, for example, here, if I know y equals 1, I will know the b vector is 0, 1, 0, 1. And for the second user, 0 becomes 0, 1, 0, 0, 1, and so on. Then the aggregator will aggregate all these bit vectors together, and finally apply this equation to get unbiased estimation. Okay. Yeah, so notice that this result is slightly less accurate than the previous one, because here is q equals 1/2, where in the previous example q equals I guess 1 over 5. So therefore this protocol is less accurate. Yeah, so the main contribution of this paper is we define the utility and maximize the utility of frequency estimation of the protocols under this LDP setting. the idea is we propose a framework to generalize these protocols and optimize some of them. And as a result, we propose two protocols called optimized unary encoding and optimized local hash. And yeah, so improving this basic task, we get better result in the more complicated ones. Yeah, so the method is we first measure utility by its variance, by the variance of the estimation. This is because the estimation first is unbiased, right? And then we, even if it's unbiased, it will vary, I guess, center the true estimation. Therefore, we measure the variance. So the smaller the variance implies the more accurate the estimation is. So we measure the variance, which is defined like here, and similar equal to q n times q times 1 over q divided by p minus q squared. Then we propose a framework called Pure, and cast the existing mechanisms into this framework. So in this framework, for each output y, we define a set of input v called the support set. The intuition is each output will vote for a set of input. For example, in the generalized randomized response, a value is randomized into another value. This value will be supporting the other value. But in the unary encoding, a value is first encoded into a bit vector and randomized into another bit vector. This bit vector will support the values in which are 1 in the location. Okay, so yeah, so if we define the support set, we kind of can generalize all the three protocols into a framework. And so for example, in another example is in BinaryLocal Hash, the support is defined as all the values that after hash will get the same result as the reported y. Okay. Yeah. So then we define P star and Q star to be this support probability, and in randomized response, P prime is P, and in others they are different. And the goal becomes an optimization problem. So the goal is to minimize the variance, which is equivalent to minimizing this amount. And but the constraint is that P prime and Q prime should satisfy epsilon LDP. Yeah, I guess if you are familiar with the classical differential privacy, pure in that setting means there is no delta notion. But here, pure just means this holds for all input and output pairs. So we kind of take this and try to optimize this unary encoding thing. And we noted that in the original unary encoding, each bit is perturbed independently with the P and Q amount. But so the intuition is to make P higher, which implies the better utility. And the key insight here is maybe we can perturb 0 and 1 differently. right? Because there are more 0 values in the bit vector, so we perturb them with higher p, and there is only one value 1 in the bit vector, so we perturb it with 1/2. Therefore, the location of the value 1 becomes random, purely random. So the value 1 will become 0 or 1 with the probability 50/50. But for the bits 0, with a very high probability, they will be preserved. So in the end, we get the same privacy guarantee, but we kind of get better utility result. So because yeah, I guess I have a typo here. Should be, yeah, this should be P1. This should be 1 minus P1. So therefore, it's 1 minus, yeah, so 1 minus Q0 divided by Q0, because this is 1/2. This is also 1/2. Cancel out. So yeah, so that's the Uniint Coding thing, and this is the optimized local hash, which is kind of the final thing. Yeah, so in the original binary local hash, the secret is compressed into 1 bit. So intuitively, the very large domain is divided into two groups. So this compression loses too much information in this step. So remember the value g here. So in the original BLH, g equals 2 groups. Right. So and also in the other step, which is called the perturbation, the p is kind of the highest that we can get. Therefore, the perturbation is pretty accurate. So the key insight here is that maybe we can balance between the compression and the perturbation steps, so that the overall information loss is minimized. But the compression loses less, but the perturbation loses more. Okay, so as a result, if we set g equals e to epsilon plus 1, we will get the optimal utility. So it's the technique is very simple. We just take a derivation of the utility and get the result. Yeah, so let's see some analytical and empirical result. So DE here means direct encoding. The variance depends on D in the denominator, and when D becomes large, the variance increases linearly. But for other
what is D again?
Oh, D is the number of possible answers, which is the size of the domain. Okay. Yeah, so SHE and THE are investigated in the paper, but I kind of ignore here. SUE is the Uniint Coding I just presented. It will have the variance of this value, and the optimized one will decrease this, reduce this value to be this one, and BinaryLocal Hash will be reduced to optimized local hash, and the variance will be reduced accordingly. Yeah. So I noted that the direct encoding has a communication cost log of D, because if you have domain of size D, you can just binary encode it. But for the unary encoding, you need log of D communication cost. For the local hashing function, the dominator factor is the index or the hash function, which costs a log of n. Yeah, so as I said, the direct encoding has a very greater variance with the larger domain. But these two have similar variance, which kind of interesting if you think about it. But ORH has less communication cost because there is no unary encoding thing. So, guess to conclude, we survey existing LDP protocols in this paper, and we propose a pure framework. And then we optimize existing protocols and come up with the optimized unary encoding and the optimized local hash. So one limitation is that the variance is linear in D, which seems inevitable as a result when the question requires a very large number of users in order to find out the significant answers. And the other one is that this function, this protocol cannot handle very large domains, because for very large domain you need to query, you need to do the calculation for every possible answer. When the domain is 2 to 64 or even larger, this is infeasible. Yeah, we will handle large domain and set values in the future. And I guess have 10 minutes or?
Yeah, you have a few minutes.
And some experimental highlights are we did experiment on the CERIAS dataset and also others. So we compare the wrapper system and the other BinaryLocal hash, which is introduced by the SOL paper, and our optimized local hash mechanism. And as you can see, as a result, the variance will decrease as epsilon increase. So this is in exponential scale. Yeah, so I guess E2 epsilon equals 4 point something is one parameter of wrapper. So as we can see, these two are the wrapper results. They have like 10 to 8 something variance. But if ORH is used, the variance will become 2 orders of magnitude better. Yeah, and another parameter is much higher, so we didn't go that far. Yeah, another is called information quality. This is the true positive number. So if we set the threshold to be like 10,000, we can get like 50 true positives. And if wrapper is used, we get 40 or something. And BLH and OLH perform similarly, but I guess in terms of false positives, OLH will only have a few false positives, but BLH will have like 50, I guess, false positives. Yeah, so that means the information quality for OLH is better. Yeah, so another interesting finding as a byproduct of this paper is if like 2 or more questions is asked, it is better to partition all the users into groups and let each group answer one separate question, instead of splitting privacy budget, which is typically used in the classical DP community. Yeah, so we found out partition users will be actually better. Yeah, and finally I will thank my co-authors and co-advisors, and I would like to take any questions you have. I guess I have more backup slides if.
Actually, I have a quick question. So you mentioned Rapport is using, I think it was 4.3. So what do you think is, reasonable value of epsilon? Do you have any opinions on the matter?
I guess like at most 4, I guess. So you type e to 4, which is already like 50 or something. So 4 or 5 will be.
Any other questions?
I guess that for that question, I guess that also depends on how much the adversary can learn from the answer.
Mm-hmm.
Right? That's a debatable issue here.
All right, let's thank Tianhao.
Thank you.